We're now going to take a look at an example that deals with a lag compensator. As always, I would encourage you to try to work through the example yourself or at least set it up before coming back to the video to see the solution. So in this example, we have a unity feedback system with a forward transfer function g of s equals k divided by s times s plus 7. So what we can see from this is that we have a type 1 system. And so we're told that this is operating such that it has a 15% overshoot. So we want to find a few things here. First, we want to find the steady state error for a unit ramp input. And so this is for our uncompensated system. So we're just saying here's the system, what's our steady state error for this unit ramp input. For part B, we then want to design a lag compensator to improve the steady state error by a factor of 20. And then in part C, we're essentially just checking our work. We're saying now that we've added this compensator, evaluate the steady state error for our unit ramp input again. Okay, so for part A, we're essentially just doing analysis like we've done previously, but let's take a look at that. So for part A, again, we know in general our steady state error is going to be 1 divided by kV for this type 1 system. So we need to find our kV. So we need our kV, and so as we had said previously, our kV is equal to the limit as s goes to 0 of s times g of s. However, if we come back up here to our g of s, we notice that we need to know that gain value k. So we need our gain that corresponds to that 15% overshoot. So corresponding to 15% overshoot. Okay, so now we're going to go back to equations we had from our transient response chapter. And so we notice we have a second order system because we have the s squared in the denominator. So it's appropriate to use these equations. So we know that our damping ratio, zeta, is equal to negative log of 15 divided by 100. So our damping ratio divided by 100 divided by the square root of pi squared plus the natural log squared of 15 over 100. And so if we evaluate that, we see that this corresponds to a damping ratio of approximately 0.517. So we could calculate this gain value that corresponds to that by hand, but it is extremely tedious. So what we're going to do is we're going to go to MATLAB. So the first thing we want to do in MATLAB is, of course, we're going to need to plot our root locus. So we want to plot the root locus, and so we've seen how to do that just using our simple rlocus command, where we have our open loop transfer function as the argument. Now once we've plotted our root locus, we're interested in the point where we have a certain damping ratio. And so this is going to be a radial line in our S-plane. So a constant radial line for constant percent overshoot. And remember, we can add that line to our root locus if we use that s-grid function. And that has two arguments. In this case, we want to put 0.517 for our damping ratio. We can just put 0 for our natural frequency because we're not interested in any particular natural frequency. So once we have that overlaid on our plot, remember we could zoom in or we could adjust that however we want. And then we can use our rloc find function. And so that's going to let us it's going to let us interact with the plot and manually select a point, and then that's going to give us back our gain and pole information. So again, we could do this by hand. It's just very tedious and not really something that you want to do, so using this approach in MATLAB is better. And so if we do that, what we end up with is a gain that is approximately equal to 45.41. So I'll note that this gain actually comes from an older octave program that I had used in previous semesters. So if you do this process in MATLAB, you might get a slightly different value for your gain, and that's okay. You might also see slight variations depending on the resolution of the gain in your plot. So remember, we can actually have a second argument here, which is an array of gain values, and in doing that we can set the resolution of gain. So based on these things, you might get a slightly different value, but it should be around 45. So knowing that value of our gain k, we can go back to this equation for our k sub v, and we can say that our static error constant kv for our type 1 system is going to be equal to the limit as s goes to 0 of s, and now our g of s, we know we have the 45.41 divided by s times s plus 7, and I've got two pluses there for some reason, so s plus 7. And of course what we can see is our s's are going to cancel out there. Limit as s goes to 0 is just going to leave us with 45.41 divided by 7, which is approximately 6.49. And then as we said above, we can find our steady state error, and so let's call this steady state error with no compensation. So steady state error no comp is going to be approximately 1 divided by that 6.49, which gives us approximately 0.154. So that would be our steady state error without our compensation. So now for part B, we want to design a lag compensator that's going to decrease our steady state error by 20%. So let's come down here for part B, and let's say we want to decrease our steady state error by 20%. And so, of course, the format of our system, or if we think about it in the block diagram, is we're just going to add that compensating block. So we're going to have some S plus ZC and some S plus PC. So that's going to be sort of our block in our block diagram, right? And so that's going to be added then to our GEQ. And so what we saw in the previous video then is we have some updated static error constant, KVN, which is equal to our original static error constant, which above I've just called KV, so that's why I'm not going to call it KV naught here, times ZC over PC. Now, if we want a 20-time reduction in our steady state error, because our steady state error is just 1 divided by KV, so as we wrote up here, we know that means a 20 times increase, or a factor of 20 increase in our KVN. So let's come down here and say that this is a factor of 20 times increase in our KV. So that means that this ZC over PC factor needs to be 20. So from here, of course, we have two variables to choose, so we can just arbitrarily choose one. So let's just arbitrarily choose a pole value, or pole location rather. So arbitrarily choose our PC to be at 0.01. And so with our PC at 0.01, that means that our ZC is at 0.02 in order to get that ratio or that factor to be 20. So if we have some updated GC for our compensated system, so this is going to be our equivalent forward path, this is going to be equal to, now we have our S plus 0.2 from our 0 times K in the numerator, and in the denominator we've added this S plus 0.01 times S plus 7. All right, so that would be the updated compensated system. Again, if we were to draw a block diagram, we would just add this block in the forward path such that it updates our forward transfer function to look like this. And of course, again, keep in mind that behind this there are some physical components, so this would entail adding some capacitors, resistors, and inductors to our network. So now for part C, we're saying what is the actual improvement. So we want to evaluate the steady state error for a unit ramp input to our compensated system. So again, what we want to do is we want to go through the same process we did for A. So we're interested in, again, still operating at 15% overshoot. So we're still looking for this intersection with this radial line corresponding to a damping ratio of 0.517. So we plot our root locus. So let's come down here and we can say for part C, we want to use MATLAB again. So we're going to plot the updated root locus. And so again, we're going to do that with that R locus function, except now we have GC as our argument as opposed to the initial G. Again, we can overlay our desired damping ratio, that radial line, using the S-grid function. And then finally, we can use our rlog find, and that's going to give us our gain value corresponding to that point that we manually select in our plot window. And so if we do all that again, you should get a gain value that is approximately 44.56. Now again, this is from an older octave code that I had written in previous years, but you should get something at least relatively similar from MATLAB. So now we just go back and plug into our KVN equation. So our KVN is then going to be approximately, so we let the limit as s goes to 0 of s times this updated g of s. So we see again that's going to cancel out with this s here. We let all of the other s's go to 0, and we're going to get 0.2 times the gain we found with MATLAB, which is 44.56, divided by 0.01 times 7. And so if we plug that in, we get approximately 127.3, and then we just invert that to get our steady state error. So we can say steady state error with compensation is now going to be approximately 0.0079. And so if we compare that to our initial steady state error without compensation of 0.154, we see that it ends up being an improvement of about 19.5 times. So improvement of 19.5 times. So a 19.5 times reduction in our steady state error.